field if we see here that the electric field always varies as 1 over r squared? Well, remember, that's just for point charges that it varies like 1 over r squared. For a continuous charge distribution, the electric field is approximately constant. So where would we see that? Well, surprisingly enough, on the surface of the Earth, we have a relatively uniform electric field near the surface of the Earth. And this is caused by, basically, by lightning. Lightning delivers negative charge to the surface, and so the Earth actually has a net negative surface charge. And then it's positive at altitude. But whenever we get a constant charge distribution over a plane, we get a constant electric field. And this is something I'll derive for you later. But you can imagine then that we have a positive charge density, then the electric field will point this way. And then there would have to be a negative up here. So this would be essentially an infinite plane. Not really infinite, but semi-infinite. And so this is one of the really important results that we're going to see in chapter 23 when we get to Gauss's law. That an infinite plane of charge produces a constant electric field. Now, is the electric field really constant? Well, not unless you have an infinite plane. But you can make it approximately constant. Just the same way as on the surface of the Earth, you can say that the acceleration due to gravity is fairly uniform near the surface. But it's actually, when you look at this on a larger scale, you see that it's actually a spherical distribution of mass. And similarly here, if we looked at this over a large enough scale, and let's say we're the surface of the Earth, or whatever, we would see that either it's not completely flat, or it's not infinite. In either case, there's no proof that anything in the universe is truly infinite. So this is an idealized situation, but it's approximately true. And so we can get the direction of the electric field just by knowing which side is positive and which side is negative. So the electric field then would point up in this situation, but near the surface of the Earth where the charge density is negative, like this, the electric field would point down. So this would be a typical field pattern near the Earth's surface. Where this is negative, and then at really high elevations we have positive. So here we could have, well, this is really the source of super lightning, by the way. Super lightning occurs when highly charged positive regions of the Earth's upper atmosphere can cause a conducting effect, which is a lightning bolt that can last like 5 seconds. It can go continuously for 5 seconds, which is kind of amazing. But here near the surface of the Earth, the electric field typically is somewhere around 100 newtons per coulomb. Okay, so that's a typical value for the Earth's electric field near the surface of the Earth. Now it changes at night because there's less negative ions falling down at night than there are during the daytime. It would change if you're not on a regular surface, if you're on a hilly surface. It would change if you walked along the surface, because if you walk along the surface, then the charge would be over your body, and that would disrupt the electric field pattern. But in these ideal conditions, the electric field would be constant. So let's take a look at a problem like this, in which we've got a deflection plate we'll make the bottom side of the plate negative. And we'll make the top side of the plate positive. And then let's fire an electron in from the side. And let's say that that electron moves at a speed of 10 to the 5 meters per second. Okay, and so that's about maybe 1/300th the speed of light. So we don't have to worry about relativistic effects here. But we'll let that electron fly through these plates. And then let's say that the strength of the electric field, now have I drawn it right here? Is this the right direction? No. Why is that wrong? You know it's got to go from positive to negative, so you can always catch yourself. You make a mistake like that by just realizing that any individual point charge is going to have its field lines go from positive to negative. And so that means that the whole thing has to go from positive to negative, even if it's a uniform electric field. So in this case, let's say the electric field is 1,000 newtons per coulomb. So this is no longer the example I was talking about here on the surface of the Earth. These are deflection plates for an electron. And so this is a way that you could deflect electrons, for example, on their way to a phosphorescent screen for a television. Although magnetic effects are also very important. And we'll get to those later. But for this problem, let's say that the distance, the length of the plates, L here, is equal to 1 meter. And let's find the vertical deflection of the electron as it moves through the plates. And let's assume that this distance is small. D here is small comparison to 1 meter. The reason why I'm making that specification here is if this distance is large in comparison to 1 meter, then we don't have an infinite plane of charge. That if we've got something like this, where this side is negative, this side is positive like this, then it's approximately infinite in that the amount that it varies is not too much different from an infinite plane of charge. But that's is only true if the separation distance between the plates is small, and then we can call this a semi-infinite plate. So it's not really infinite, and as I said before, there's no real infinities that have ever been proven to exist anywhere in the universe. And maybe there are infinities, but we haven't proven that there are. We use infinity in mathematics as a very convenient tool to solve problems. But to actually have an infinite amount of whatever is, this is very problematic. And it's not something that we have any evidence for. Okay, so what do? Well, the first thing that we do, because the electric field is constant, this means, and I'll bet you thought that you didn't have to think about this anymore, this means you can use your constant acceleration kinematics equations that we have in physics 2.8a. So this means that if the electric field is constant and force F is equal to QE, where Q is the charge on an electron, and E is our constant electric field, due to an infinite plane of charge, then that must also be equal to ma by Newton's second law. F equals ma. Okay, and so this tells us then that if the electric field is constant, then the acceleration is constant. So that's if and only if E is constant. And so what we've got is something that's kind of like a gravity problem. We take a mass and we fire it horizontally this way through a gravitational field. We should be able to find out what its vertical deflection is before it hits the ground. And so we'll do the same thing here. This is just an example. One of many, many that we'll be looking at where we are using the exact same equations as we used in 288, but just to solve an electrical problem. Okay, so if the charge comes in horizontal, so this is a horizontal velocity, it has no components in the vertical, then what can we say about the acceleration in this direction? In which direction? In the x direction, the acceleration is 0. Good. And in the y direction, the acceleration, a, is going to equal EQ over m. Okay, and so we know what E is. Q is the charge on an electron. So that's minus 1.6 times 10 to the minus 19 coulombs. M is the mass of an electron. I'd have to give you these. 9.1 times 10 to the minus 31 kilograms. So we plug those in, and that'll give us the magnitude of the acceleration. I'm not going to talk about the direction yet. Let's just get the magnitude first. So this is going to be 1,000 Newton per coulomb. 1.6 times 10 to the minus 19 coulombs divided by 9.1 times 10 to the minus 31 kilograms. See what kind of acceleration we get for that. Okay, so that, wow. 1.75 times 10 to the 14th power. And so what would the units for that be? Well, it would be Newton per coulomb times coulomb divided by mass. That Newton is kilogram meter per second squared. I'm sorry, mass here is going to be kilogram. That'd be kilogram meter per second squared. Coulombs cancel, so that's just meters per second squared. That's our normal units for acceleration. So how many times the acceleration due to gravity is that?
A lot.
Well, it's more than 10 to the 13th power times the acceleration due to gravity. Okay, so it's more than 10 billion times the, 10 trillion times the acceleration due to gravity. Okay, but electrons don't care. They're just these little guys that they can accelerate like that. And it's moving pretty fast, so let's see how much it's going to deflect over a 1 meter distance. Which way is it going to move, up or down? It's going to go up, not down. So that, the gravitational analogy then doesn't necessarily hold in terms of the actual trajectory. The trajectory could be parabolic up or parabolic down. And so what we're interested in as it moves through here is this delta y displacement from its original position. How much is it deflected vertically? That's my delta y there. So that's what I'm solving for. I've got the acceleration, and so what do I need then to get the vertical deflection? Time. You need the time that it takes to move through, because that's how much time it has to accelerate. And so what we would want to do is go back to our original kinematics thing, and if you had me for 2.8a, this is the way I recommended that you do it. Set it up with knowns and unknowns here. And then for the x motion, we just have v times t equals x. Or x in this case is the length, L, which is 1 meter. There's no acceleration in the x direction. So vt is equal to L. So that means we don't know how long the acceleration is going to act. But these are our y motion equations that we're going to look at here. So in terms of knowns, we've got v0y is equal to what? 0, not 10 to the 5. That's the x initial velocity. But what we're doing here is we're saying that this is equivalent to how far is this electron going to move this way. If we allow it to act for an amount of time, that's the time that it takes for it to move through the plates. So v0y is not 10 to the 5, it's 0. Very, very important there. Acceleration A, we know that. We just solved for that. That's EQ over M, 1.75 is 10 to the 14 meters per second squared. And then, what else do we know?
We can find time.
We can find the time. Good. Okay, so we don't know, so far we don't know time, and we don't know the final velocity, and we don't know the y displacement. So we don't know 3 out of 5. We're in a little bit of trouble here unless we realize that we can get the time of flight from our x equation. Then we can proudly put that time of flight over there in our known column. Then we know 3 out of 5. Okay? And so that's the way that you learned how to do this in Physics 2.8a. They were just problems like you had a motorcycle that shot out along a horizontal path, and then what was this vertical drop when it hits, before it, we did that like in a lab, remember, we fired it horizontally. Okay, so that's the same problem here. Okay, so what we need then, T, is just going to be L over V, and so that'll be then 10 to the minus 5 seconds, or that would be 10 milliseconds. And so now we can eliminate all of our equations involving v final y to get the net vertical displacement. Okay, so we've got our 4 kinematics equations. Let's write them down again. V final y equals v0y plus at. Delta y equals 1/2 times v0y plus v final y times t. Delta y, v0yt plus 1/2 a t squared, and v final y squared equals v0y squared plus 2ay. So those are our relevant y equations. We get rid of all the ones that involve v final, because we don't want that. We weren't asked for that. We were asked for the delta y. That's all we wanted, the vertical deflection. So that means that we can choose the third equation to get that. And this simplifies nicely because v0y is 0, so we don't have that first term. So that gives me delta y is 1/2 a squared. And then, so we just read that off of our table. A is 1.75 times 10 to the 14. Meters per second squared times, and then here, for the time, we've got 10 to the minus 5 squared, so that's 10 to the minus 10. So that gives us 1.75 over 2 times 10 to the 4. So, a little bigger than I wanted, but that's okay. 1.75. That's going to be 8.75 times 10 to the 10 meters. Or 10 to the 4. Yeah, 10 to the, this is 0.875, and then this was 10 to the 4. Okay, so that's the procedure. The number here is a little big for what I wanted, but that's okay. That's the correct procedure. Any questions? Okay, so that's typically the way that you might want to handle a problem with a constant electric field that looks like that. What if we had one that looks like this? Let's say we've got a charge of 1 coulomb. And by the way, a charge of 1 coulomb, if you had a charge of 1 coulomb, and then you put a charge of minus 1 coulomb on the Great Pyramid of Egypt, you could lift it up. That's how strong the electric force is. So even though that amount of charge goes through an electrical instrument per second, you separate that amount of charge, you could lift a huge amount of weight gravitationally. Nevertheless, I'm going to use that number here because it makes the math a little easier. So let's say we've got a 1 coulomb charge, and the length here of this string is 1 meter. And let's say we have an electric field, this is plus 1 coulomb. Let's say we have an electric field that points to the right like this. And let's say that electric field is equal to 10 to the 5th power newtons per coulomb. Pointed out to the right like that. And under the influence of this, let's say that we have that this thing has a mass m. Let's set that mass equal to 1 kilogram. Let's find the equilibrium angle of this thing from the wall. Theta and the distance here, which we could call x. Okay, so how do we do that? Well, first of all, this is going to be similar to our pitfall problem that we did last time. the lab. Except here, you're just going to have the forces that you're interested in are going to be on this one object. And so you're going to have a force. Now, is that force going to point this way or that way? The electric field is pointed straight out. It's going to have to point to the right. So that means that we can just kind of put little positives in here to indicate that this is like an infinite plane of charge. Because we know that the electric field is going to point away from positive. And then that means there'd have to be a negative way out here, really far away somewhere. So we can see then that it'll tend to repel positive and be attracted toward negative. So that shows us then that the direction of the electric force is this way. The tension in the string will be this way, and the force of gravity will be this way. Okay, so what we can do then is, well, we can figure out what the components of the tension are that support the weight. So if this is T, then this is going to be T cosine of theta. Okay, so this angle here then would be theta. And then the part that fights against the electric force would be T sine of theta. And that would point in that direction. So you could say then that in equilibrium, the sum of the x forces is 0. And the electric force here is going to be the charge Q times the electric field, which is constant. Okay, so you can say then that the sum of the x forces is going to be QE minus T sine theta equals 0, because we're in equilibrium. Similarly, for the y forces, we can say that T cosine theta minus mg is equal to 0. And so then we can eliminate the tension from both of the equations by just, and this is the same trick that I used in lab last week to do this for the pith ball problem. You can write this as T sine theta equals QE, and T cosine theta equals mg. So that's just rewriting those equations, but we're doing it in a way that allows us to divide the two equations. So you see, we've got two problems here. One problem is that we've got the tension that we've got to get rid of. And the other problem is that we have something that's a function of sine and cosine at the same angle. So we could combine them all together. Another way of getting rid of one of these quantities would be to square this one, and add them. Then that would get rid of the theta, and this would go like cosine squared plus sine squared, which would be 1. Then you'd have something that involved just the tension on these things. But in this case, since I'm not asking for the tension, what I want is the angle and the distance when it's in equilibrium. I'm just going to divide them. That gives me the tangent of theta is equal to QE over mg. And so in this case, that's 1 Coulomb times E, which is 10 to the 5. Let's make this, let me see here, 1. Let's make this, make it 1 Newton per Coulomb, just so we have a little more reasonable number. So 1 Newton per Coulomb divided by m, which is 1 kilogram, times g, which is 10 meters per second squared. Okay, so theta then would be the inverse tangent of 110. and that would give me 5.71 degrees. See, the problem I had here was that this 1 Newton, with just a very small electric field, you got a gigantic force, so this thing would pretty much go horizontal, and you wouldn't even hardly notice the effect of gravity. So I wanted to make the two somewhat comparable. So here we have 5.71 for the angle, and so then we can say that x over L is equal to the sine of 5.71, or x is equal to 1 meter times the sine of 5.71. So that gives me about 0.1 meters. Okay, so that's how far it is away from the wall. This is the angle. What we did here was we just set this up as a static equilibrium problem in which the tension had an x component that balanced out the electric force, and it had a y component which balanced out the gravitational force. And then we just solved the two equations simultaneously. We eliminated the unknown tension, got everything in terms of a single function of theta, then took the inverse tan, and we're done. Any questions about that? All right, so next time what we'll do is we'll look a little more at electric field lines, and then we'll start looking at electric fields for continuous charge distribution. So if you want to read ahead for Thursday, we're going to be looking at E for the ring, the line, the disk, and the plane. So we'll be looking at the basic idea of how to do the electric field for continuous charge distributions. And we'll be using these examples. And so a lot of times this is where people start having trouble. And so this is why I'm kind of giving you a little heads up here to read through all of chapter 22 and see if you can follow through the examples. And I'm not going to go through anything that's really much more difficult than what the examples already are in the book. So that can help get you going if you can do that introductory reading. And then we'll have some group quiz activities that will help to reinforce these ideas also on Thursday. One other thing, because there's no Friday lab, that means there's no Thursday lab either this week. We've got no lab. And a reminder that that also means that Friday, Monday, Tuesday, next week there's no class. So we won't have a class again next week until a week from Thursday. So we'll have this Thursday and then a week from Thursday. So I know you're all really disappointed. It's hard to get your party hats on with a quiz. All right, so here's the quiz. I'll put, here's a equation sheet too. So I'll put some of them on each side like I usually do. If you have, if you need more paper, there's paper sitting out here. And don't forget to turn in your homework.